Hello, students. Welcome to 13.3 homework. And in this section 13.3, we have 1 to 2, 4, 6 to 8, 10 to 13. So we have some questions here related to the Pythagorean theorem. Let's take a look. 1 to 2 and then 4. So 1, find the length of the following segments. This is totally Pythagorean theorem. And just like we decomposed previously into smaller shapes, here we can decompose into right triangles. So form right triangles, and you'll be able to find the side lengths and then use the Pythagorean theorem to find the length of that line segment. And the same is true in number 2. So notice this one is probably a little bit trickier because we don't have that type of shape. But here's what I want you to do. Make the variable that you do know how to find. You can find it for this first one because I have 8 and 10, so I can find y. And then for the larger triangle, I could ignore that totally and say 8 and 17, and I can find this whole length. And then, of course, just cut off the piece that you know, which is y. Same for each of these. Let's see here. Right square pyramid. And again, it says use the Pythagorean theorem to find each of the following. Okay. Now here they want you to find x. Now notice it looks like you have to do something with the height of the entire pyramid. You don't. We're looking for this. We'll need that eventually, but you should be able to find this whole length by thinking of this as a right triangle here. Okay, so keep that in mind. Let's see here. What else? Same over here. So right triangle, right triangle. They're all right triangles. And they should be because we're using the Pythagorean theorem. Let's see here, 1, 2, then, now these are still part of question 2. So again, this is a cube. And this one tends to be a little bit problematic for students because we're trying to find the diagonal of the cube that goes all the way through the middle. So what I would recommend that you do is create a right triangle just on the base first so that you can find like this thing, call it y, and then you'll have the height because you know it's a cube. You have this one, and then you have a second right triangle. So you have 2 right triangles. This is use a Pythagorean theorem twice. Okay. And this one's really, 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 really nice because we get to use what we did with similar triangles out of 12.4. These are similar triangles by angle. And so you should be able to find the ratio of the side. So solve for the missing piece here because it's a right triangle, and then use ratios to come up with the difference. Very cool. Next up, on a 4x4 geoboard, the greatest perimeter of any square is 12 units. Find a polygon on the geoboard with a greater perimeter. So a 4x4 geoboard, remember, think about like the nails, right? 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and it says the greatest perimeter of any square is 12 units. Well, 4 plus 4 plus 4 plus 4. The question is, can you make a shape that has a bigger perimeter, but it has to be a polygon still? Okay, it still has to be a polygon. So keep that in mind. That doesn't mean the area is bigger. It just means that the perimeter is. Okay. Let's see here. What else? 4, so 6 to 8, and then 10 to 13. Let's take a look. Oops, done with that one. 6, a door is 6 foot 6 inches tall and 36 inches wide. Can a normal piece of plywood that is 7 foot by 8 foot be carried through the door? So when you're sketching this out, sketch out the door frame like this, but think the piece of plywood, you don't have to hold the piece of plywood vertically, right? The piece of plywood doesn't have to try to go through like this because it won't fit. It's too tall. It's 7 feet tall, but the door is only 6'6". So instead of doing that, think about, can I bring the piece of plywood through at a diagonal? And if you've ever done this when you're moving furniture, sometimes like you'll take your bed, you have to tip your bed sideways, the mattress, to kind of get it through the door. That's what we're talking about here. Will it fit? And who knew there would actually be math that could help you as you're moving your furniture. Now, let's see here. Determine whether the given numbers represent lengths in the sides of a right triangle. Okay, I'll let you try those out. Again, Pythagorean theorem, in this case, the converse of the Pythagorean theorem. What's the longest piece of dry spaghetti that will fit in a cylindrical can that has a radius of 2 inches and a height of 10 inches? Draw this one out. I'm not even kidding. So if you think about it, draw a can like this, right? And you want a piece of dry spaghetti. Well, the dry spaghetti can go up to the tip top here and then go all the way across. Think about what kind of a right triangle could you build where the hypotenuse is that dry spaghetti length, right? That's my nudge, nudge, wink, wink on that one. Let's see here. What was it then? 10 to 13. So an access ramp enters a building 1 meter above the ground level and it starts 3 meters away from the building. How long is the ramp? Sketch out the triangle. It's a right triangle. You should be good to go. To make a home plate for neighborhood baseball park, we can cut the plate from this, shown in the following figure. Okay, those are 12 and 12. Got it? What's the question? If A, B, and C are the midpoints of the sides of the square, what is the length of the side of the square to the nearest 1/10 of an inch? Well, we know we need 12 inches on those pieces. These are the midpoints, it said, right here and right here and even right here. But if they're midpoints of the square, that means that these three links, that all these links right here, they're all the same. So this is an isosceles right triangle, and we know something about that ratio. Remember the ratio 1 to 1 to √2. Set up a ratio. The fact that you know one side is 12 inches, it's the long side. So you'd have 12 inches is to x, that's the short side, as the square root of 2 is to 1. Set up your ratio and you can solve it fairly quickly. You may not need to use the Pythagorean theorem for this one. In a sense, we are using it, just kind of in a shorter way. Next up, now they're asking us to find the area. So we know we have to find the base and the height. And then we use 1/2 base times height because this is a triangle. So the area is 1/2 base times height. Here I have the base. Here is the height. And I'll let you think what is the height for that and then use this formula. Here the bottom is S. But this is an equilateral triangle that's been split right down the middle, which means I have a 30-degree angle. Oops, 30-degree angle at the top, a 60-degree angle down here, and there is a wonderful ratio of those sides. And that's what we talked about before. Use that ratio to find the missing piece, and then use all of those pieces to form the area. Use the following two rhombuses have perimeters that are equal. Okay, that makes sense. Use the properties of a rhombus to find the area of each rhombus. Aha, okay. So what we will need to do is, got it. So all the sides are 5 centimeters long. And there's going to be, basically, you can think of making 4 triangles here and 4 triangles here. Find the area of one triangle and then use it to find the rest. Find the missing pieces. 15 through 19 is next. On a baseball field, 90-foot square, if a player standing on third base throws on a straight line to the player on first base, how far is the ball thrown? Now, again, they're not showing you a picture of this, but they're telling you it's a 90-foot square. And it's tipped sideways, but that's not critical. So it's a square. Each side is 90 feet. And so a person standing on third base is going to throw across to a person standing over here on first base. The question is, how far is the ball thrown? What is the distance across that piece? And as a big hint to you, very similar to what we did on question 11, this is an isosceles right triangle, and there is a ratio that you can be familiar with to make your life a lot easier. Use the following drawing to prove the Pythagorean theorem by using corresponding parts of similar triangles. Big hint, question 16 is assigned because we did it in 12.4. And I know that some of you struggled a bit with it, but I want you to come back and say, I can do this. I'm going to make my ratios and prove the Pythagorean theorem. And I would say 15 through 19, okay? This is a beautiful proof of the Pythagorean theorem. Notice The outside shape is, well, it sure looks like a square. Big hint, you do have to prove to me that it's a square. So think about angle 1 plus angle 2. Is that 90 degrees? You do have to prove that. Once you prove it, you'll have c squared. And the question, it looks like it's equal to 4 of these triangles that are 1/2 b times a. Plus, there's a little square in the middle. And the little square in the middle comes from taking this long length of b and cutting off this piece of a. And so what we have is b minus a quantity squared. Do a little algebra on the right-hand side. See if you can prove the Pythagorean theorem. Next up, semicircles are constructed. Your goal, if you watched the video that I made for this section, I showed you that any shapes that are similar would work. It doesn't have to be squares. So find the area of each of these based on the side lengths. Remember, this is a diameter. So what's the area of a circle? Take half of it. And then add the two small ones together and show that it equals the long one. Don't forget, a squared plus b squared does equal c squared, but can you use that in this case for your triangle? And question 19, find the perimeter of the triangle with these vertices. This is the Pythagorean theorem. I know you can do it. You do not need to memorize a distance formula. You can use the technique that we've shown, that I showed in the video, and that I'll also show in class. And last is 23, Michael Jordan. Oops, up here at the top. Find the equation of the circle with the center and radius. Again, this is something that we did cover both in the video and I'll show briefly in class. It's not an excessive one. And again, it looks very similar to question 24. We should have some usefulness there. So that takes care of the homework out of 13.3. I hope this is helpful. I think the Pythagorean theorem is it's obviously one of the coolest theorems. We tend to use it an awful lot because right angles, when you build them, triangles tend to be pretty rigid, and right angles, they just aesthetically pleasing. So we want our walls in our home to be straight up and down. And I remember, like, I'll never forget, because I was trying to work a construction job when I was younger, and I thought I was intelligent and really, like, I could figure this out. It can't be that hard. And so I remember trying to figure out if if these two like if I had assembled the walls so that they would be perfectly like right up and down, when you're building these, you oftentimes will have the wall assembled and you'll have to like lift it up, and then you'll have to make sure that it's at 90 degrees, and then you kind of hammer it into place here. So you brace it and you lock it in at exactly 90 degrees. So what I was doing is I was coming out from the floor and I was coming up on the side, right? And I was trying to measure this length L, or I'll call it A, and this length B up here, and I was trying to do this, and like I was almost getting my calculator out. We didn't have cell phones back then, but I was like, okay, I can prove this. And the guy comes up to me and goes, "What the hell is taking so long?" And I said, "What do you mean? I'm making sure this is straight up and down." Oh my gosh. So he did something so quick. And I thought, okay, we're doing the same thing. His is just so much faster than mine. So what he did is he made a mark on the wall. He made a mark on the wall that was 4 feet up. He just put a little tick. And then on away from the wall where it was going to be, he put 3 foot. And then he put his tape measure. He kind of had me stand right there and he held his tape measure until the tape measure showed exactly 5 feet. So you'd actually move the wall. You'd move the wall back and forth until this one was exactly 5 feet, because it's a 3, 4, 5 triangle, and 3 squared plus 4 squared equals 5 squared. And it was done. I can't tell you how fast it was. It was like, go up here, mark, you mark, you mark, and then you just go. This is where we want it. Okay. And he's like, push it towards me, towards me. Once it hits 5 feet on his tape measure, he's like, now hammer it in. And it was it was so fast. It was so fast. And I'm sitting there looking like an idiot because I'm trying to calculate the Pythagorean theorem, and he's laughing. He's like, "You college kids, I don't know what they're teaching you over there. Um, they're teaching me the Pythagorean theorem, and I know it, but I was doing it wrong." Anyway, hopefully you can laugh at me trying to be trying to be very precise. All right. Anyway, I hope you have a good rest of your day. Off you go.